This video is about more complex stack and queue operations. We're going to focus on two exercises in this video. For the first exercise, we'd like to write a method named removeAll that accepts a queue of strings as a parameter, as well as a target string that's meant to be removed. And the goal of your method is to remove every occurrence of that value from the queue. So if I call removeAll and I pass the letter A, I'm saying look at all the elements of the queue that are A's and remove them all. So at the end of the call, only the non-A elements should remain in their original relative order. So this builds on the material from the previous video about basic queue operations. We need to loop over all the elements of the queue and find the ones that are equal to this target value. Now, the elements that aren't A's shouldn't be removed. We need to keep them. We need to retain them in the queue. But remember, we can't really just loop over the elements of a queue the way that we would with a collection like an array list. We have to remove the elements from the front, examine them, and then potentially add them back to the queue. So I think the overall strategy we want to follow here is remove an element. If it's an A, leave it out. Remove another element. If it's an A, leave it out. Remove this element. Since it's not an A, we want to keep it, but we can't just put it right back where it was. The only place that we can put it is to add it to the end of the queue like this. But if we keep doing that for all of the elements, then eventually the net effect is that we'll keep the non-A's and remove the A's. Let's try to write this algorithm together. If we go to our code editor here, I've got a piece of code already written in the main method that creates the queue from the example in the slide. And now I'm going to call removeAll queue A. Let's write the removeAll method. Takes as a parameter a queue of integers named Q. And we're going to return void, which means that our method is modifying this queue parameter that was passed by reference. So it seems like the overall operation that we're going to do repeatedly is to extract an element and decide whether we want to keep it or not. Oh, excuse me, this is a queue of strings, not a queue of integers. Thank you. And let's write the operation to look at one element from the queue. To process one element, let's make a string named element, and let's set that equal to queue.remove. That means to remove from the front. I'm going to go up here and copy this picture of the queue so I can look at it while I'm working. There we go. So in this case, we're going to remove this front A like that, and element equals A. And now we have to decide whether we want to add it back into the queue or not. Well, if it's an A, we don't want to add it back in. So we'll say if it's not true that the element equals the target value. Where does the target value come from? Well, that's a parameter that we need to pass here, string target. That's the other parameter to our method. This A becomes that target in our example here. So if the element we're looking at doesn't equal that target, then we will add it back into the queue. We'll say queue.addElement. Okay, that's the operation of processing a single element. We have to do that for all of the elements. Now, how do I do it for all the elements? Well, we have to wrap this in a loop. And of course, there's different ways to process a queue. One way is to loop until the queue is empty. But I hope you'll see that that strategy isn't going to work very well here, because our code should never end up with an empty queue, because we're going to retain elements like B and C. So we're never going to get to empty. So this isn't the right way to go. So instead, I think we need to use a for loop over each of the elements. So a kind of a novice way of thinking to do this would be to say for int I equals 0 and I is less than the queue size. We could do it that many times. That might work. Let's try it. We've already got the code in main to call the method, and we've got the code for the method. Let's print the queue and call the method, and then print the queue again. So let's see what the method does when we run it. I compile, and what have I done? Oops, I've declared it as a queue of integers again. I've got integers on the brain. Let me change those to strings, save, compile, and run again. And okay, what do I have here? Well, it says that the queue changed from this starting contents to this ending content. Now what happened? We've got some A's still left in here. What's going on? It looks like it definitely removed several of the A's, but not all of them. What happened? Well, this has to do with something that came up in the previous video where we talked about for loops over the elements of a queue. Now, it's not very common to loop up to queue.size like this. Instead, what's much more common is to make a variable named size and loop up to that variable. Now, why is that different? Well, first of all, just for a moment, let me run this program, and you'll see that just that change totally fixed the bug. All of the A's are gone. Why did such a small change make such a big difference? Don't these things seem to be the same as each other? Well, it has to do with the fact that the queue size is changing as the loop is running. So if I grab the code and put it back the way that it was before, let's trace through the code to understand why this way doesn't work. At the start of the code, the queue looks like this. What is the size of the queue? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the queue size is 10. So we're asking whether I is less than 10 in this loop here. But you have to remember that after each pass of the loop, we wrap back around, and before we re-enter the loop, we re-evaluate the loop test, which calls q.size again. It's important to remember that. q.size gets called every time as we wrap around in this loop. Okay, well, what's going to happen if elements are being removed without being added back in? If we process this A and this A here. So let's think about what we're doing here. As we remove this A, int I is going from 0 to 1. So now we remove this A, and int I goes to 2. We remove this B and re-add it to the end, and int I goes to 3. We remove this C and add it to the end, int I goes to 4. Keep in mind the queue size is now down to 8. We remove this A, we don't re-add it. Queue size is 7, I goes up to 5. We remove this C and add it. I goes up to 6. We remove this A, don't re-add it. Queue size goes down to 6. I becomes 7. And now look, int I has passed queue size. That causes this loop to stop. But really, we didn't process all of the elements. There were 10 original elements in the queue. The problem is that int I, we basically wanted int I to go from 0 to 10 because there were 10 elements. But as the queue was shrinking, that also shifted the boundary that int I was going up to before stopping our loop. And we don't want that. So what we really want to do, I'm going to hit undo a bunch of times here. We really want int I to go up to 10. So if I make an int variable set to 10, and then I go through my collection and I remove an element, it goes down to 9, I++. I remove another element, it goes down to 8, I++, and so on. I'm just always going to go up to 10 instead of going up to 8 or this other moving target here. That's why it's so important to have this int size variable. So I'm going to put this diagram back the way that it was, and I'm going to declare int size equals q.size, and I'm going to loop up to that variable's value. Compile it and run the code again. And this time all the elements to be removed are absent. Let's look at another exercise together. Exercise 2, let's write a method named isSorted. This method accepts a stack of integers as its parameter, and it returns true if the elements of that stack are in ascending order from top to bottom. Remember that when a stack is printed, the bottom is usually on the left and the top is usually on the right. So the 10 here is on the top. This stack S1 is sorted because if you look from top to bottom, it goes 10, 20, 30, 40. And this one here, S2, is not because, well, these two are sorted, these three are sorted. Oops, this 2 is not sorted relative to the 6. That one's out of order, so isSorted S2 would return false. How do we do it? Well, let's go back to our editor for a moment, and let's go up here to the main, and let's declare a stack. Let's add some values to it by pushing. So I'm going to push them in reverse order so that they're sorted. 50, 40, 30, 20, and 10. Okay, and now I'm going to ask system out println stack. I'm going to ask whether the stack is sorted. And I'll print the stack again. Okay, let's write this method. Let's go down here and let's write a method heading that says public static. Remember, this one is returning true or false, so it returns Boolean is sorted. takes a stack of integers named stack. How do we do it? Well, we just need to look at the neighboring elements. If the stack stores 50, 40, 30, 20, 10, we need to look at the 10 and the 20, and then we need to look at the 20 and the 30. We just need to make sure that each pair is not out of order, and then if all of them are in relative order, then the whole thing is in relative order. Okay, well, one issue that might come up is what if the stack is empty and there are no elements? Maybe that's a little bit tricky. So we could do something like if the stack is empty, we could just decide that that is sorted. But otherwise, let's grab elements and then compare pairs. So let's grab the top element, int prev equals stack.pop. That's going to be the 10 in my example here. We're always going to compare the previous element to the next one. So maybe we could say something like, while the stack is empty, let's compare prev, which in our case would be 10. Let's compare prev to what's on top of the stack and see if they're in relative order to each other. So for example, if stack.peak, the thing that's on the top of the stack, is less than prev, that means they're out of order, right? If what's on top of the stack, excuse me, my editor moved out of the way. If what's on top of the stack is smaller than prev, that's bad. That means not sorted. So that means we should return false. Otherwise, what we need to do is update the prev to be the 20 and continue comparing to subsequent elements, 30, 20 to 30, 30 to 40, 40 to 50. So otherwise, let's set prev to equal stack.pop. So remove out that top element and set him to be the previous element. Okay, looks pretty good. If we get all the way to the end of this loop and we've looked at every element from the stack and none of them were out of order, then it must be in order, right? So if we get down here, we'll just return true, sorted. Let's try out our method. I need to, excuse me, I think I've used the wrong syntax here. I wrote stack.isSorted. That would be the syntax if this were a function inside the stack class, but it isn't. It should take the stack as a parameter. I'm going to comment out this Q code that we wrote a moment ago, so that all we see in the output is this result of calling isSorted on the stack. So I run it 10, 20, 30, 40, 50, and it says true. Great. But one thing about this output that's subtle is a big problem. Look at this line of output right here. This is an empty stack. Do you see? After we called isSorted, we printed the stack again, and there's nothing in it. And that should make sense, because if you look at our code for isSorted, we loop until the stack is empty. We empty out the contents of the stack, right? Well, this is a problem, because if the client calls this method, they may not want us to destroy the stack. They want to know whether their stack is sorted or not, but they don't want the stack's contents to be lost in the process. So if you look back at the slide of the problem description, it says your method must not destroy the stack, and you may use a collection as auxiliary storage. So what we need to do here to totally finish working on this problem is to make sure that at the end of our method call, no matter what, the stack's contents are restored to their original contents from the start of the call. How do we do this? Well, basically we just need to keep another collection that stores a backup of these elements. Now, it's a little bit subtle, but you may think that you can do something like stack integer stack2 or s2 equals stack. You might think that you've made a backup copy, but I hope you understand that this doesn't make a copy of the stack. This just makes another reference that refers to the same stack. So if I look at S2 later and stack has been modified, then S2 will also be modified. So this line of code that I've written here doesn't make a backup copy. Instead, what I'm going to do is I'll make a new stack of integers. And as I remove things from the original stack, I'm going to put copies of them into S2. I'll say s2.push prev. Every time I do a pop, I'm going to make sure to put him into the backup stack. In fact, maybe just to make it really clear that he's for a backup, why don't I call him backup? And I'll say backup.push prev. Okay, now, as I'm peeking, I don't have to do anything with the backup that involves peeking, because peeking doesn't modify the stack. Here I say prev equals stack.pop, so again I need to say backup.push prev. And then when I get down to the end of the code here, I need to restore from the backup. So I need to say, while the backup isn't empty, let's push onto the original stack the result of calling backup.pop. And if you're thinking about the ordering, the element ordering, keep in mind that if you copy from one stack to another, it does a reversal. But if you do it twice, it will double reverse and put things back into their original order. So the backup going back into the stack will put things there in the right order. This is mostly correct. The only case that we don't handle well is this one right here. If we return false here, we're immediately going to exit the method, so we're never going to get to this code to do the restoring. So I think the smart move is to make sure that we always get down here to the bottom of the code. I think the easiest way to achieve that is to use a Boolean flag here. Boolean sorted equals true. Now, if I ever get to this point in the code, this means no, it's not sorted. Something is out of order. So instead of returning false right away, I'll just say sorted equals false. And now I want to stop my loop. I don't need to look anymore. If I know that it's not sorted, I can just stop. So there's a couple ways of doing it. You could say break here. Some instructors don't like to use the break statement. So if you don't want to use a break statement to stop the loop, you could say something like while not empty and sorted. So while I still haven't seen any problems, I want to keep my loop going. But if I ever turn the sorted to false, I'm going to stop the loop right away and not continue. But then down here, I'll restore no matter what. And what will I do here? Instead of returning true, I'll return sorted. So in other words, if I found no bugs, no problems with the sortedness, then sorted will be true. But if I did find any problems with the sortedness, sorted will be false. And that's what I'll return at the end of the method. So let's compile this and run it. I see 50, 40, 30, 20, 10. True, it's sorted. And then afterward, I still have the original stack maintained intact. Now, just to test it with a stack that isn't sorted to make sure that this case doesn't break anything, let's go up here and make a quick change. Let's move this element here. So now they're out of order. 10, 20, 40, 30, 50. If I compile that and run that, sure enough, after the code is done running, the stack is still there in its original order.